Hello everyone, I'm Tomita Shusaku in Nara Institute of Science and Technology. I introduce our new method, FedTour. In recent years, tourism services tend to use AI. AI enables tourist spot context recognition. For example, AI can inform us not to visit congested areas. At the same time, we can automatically get tourist spot notifications from currently trending events. Object recognition models for images and videos are effective in recognizing the complex context in tourist spots. Since there are various attractions and landmarks, it is difficult to sufficiently train the model using only open source data. Therefore, it is desirable to use not only open source data, but also photos taken by tourists as learning data. However, when tourist photos are collected through the internet, there is a possibility that private data will be exposed either due to attacks or mishandling by third parties. Thus, there is a need for learning methods that combines privacy protection and data training. Federated learning allows us to train the models while keeping the data private. In federated learning, edge devices like smartphones trains on their own data and sends their models to aggregation server. The aggregation server integrates the models and then sends the new model back to each device. Each model runs data from all devices in directory through repeated loops of training on edge devices and integration on the aggregation server. Data in devices are not exposed to external servers, which makes federated learning advantageous over other techniques. However, since models are large, mobile devices will consume too much power if they need to communicate with an aggregation server at a high frequency. To reduce such power cost, an ingenious federated learning should use direct communication between devices, thus avoiding the need to communicate with the aggregation server. Opportunistic federated learning is one approach to avoiding the use of aggregation servers. In this method, when two devices encounter each other, they compare data distribution. If the distribution is similar to each other, they exchange gradients and update their models. It is a method that allows for steady learning because local models are sequentially updated against each other's data. The model can steadily learn the data because it updates using the gradient from the data in the encountered device. Experiments have shown that accuracy improves as the number of encounters increases. However, this approach doesn't consider device power consumption, and it assumes that communication and updates are inexhaustible. Thus, this method can easily drain the mobile device, which is especially crucial for tourists. Conventional methods require devices to consume a large amount of power to improve models. In our method, FedTour improves model performance as much as possible while reducing power consumption so that tourist mobile device can train tourism object recognition model. We propose FedTour. FedTour is a distributed federated learning approach that enables moving mobile devices such as a tourist smartphone to efficiently train models. This method utilizes short range and few communication between devices, does not use aggregation server, We assume the following use case for FedTour. In this scenario, the assumed environment is a tourist area in Nara Prefecture in Japan, where tourists and local residents move through Nara Park and other tourist areas. People have a mobile device such as a smartphone. Digital signages are also in its spot as fixed devices. We assume that these devices have a tourism object recognition model that are already pre-trained on their own data. In one scenario, we have C1 located on the left side of this slide. C1 will encounter other devices as he goes through each spot. Tourist C1 communicates with other tourist devices and trains its own model using FedTour. Based on the use case scenario, FedTour should improve model performance while limiting communication and model updates. We propose two goals that FedTour needs to accomplish. First, FedTour must reduce the number of communication between devices, which further increases power consumption. The second goal of FedTour is to allow devices to only communicate and exchange weights with helpful devices. In other words, those devices that will improve the local model. In opportunistic federated learning, when two devices encounter each other, they communicate gradient data with the same size as the weight parameter in model and update their model. They communicate each other's updates repeatedly, allowing for steady learning. However, this requires communicating multiple times, which consumes device power. In our approach for goal 1, suppressing communication between devices, each device only sends weight parameters of their own model and updates the model through simple averaging. In this approach, a single exchange with a neighboring device is enough, so communication and updates can be reduced, saving power. To achieve goal 2, the tourist device predicts the change of accuracy of the resulting model in case it exchanges with the passing device. The tourist first receives the accuracy of the encountered device. Their predicted accuracy is generated, and if the predicted value is higher than certain threshold, the tourist device then proceeds to receive the weight parameters from the encountered device. However, if the predicted accuracy is lower than the threshold, the tourist device doesn't receive parameter. The device can decide whether to accept or not weight parameter. For the prediction, we use an accuracy change prediction model, which predicts how much the accuracy will change given two different accuracies. The accuracy change prediction model outputs the change in accuracy before and after the current update of our model from the accuracy values of the two passing devices. This prediction requires accuracy of the model from passing devices. However, since the accuracy value size is negligible compared to the weight parameter, we don't consider the power required for this communication. To obtain the prediction model, we collected accuracy change data before and after updating various accuracy models based on simple averaging. We used VGG16 that trained Schwarten dataset, which consists of 10 kinds of objects in this collection. This scatter diagram shows the inclination. The main inclination that can be seen at a glance is that higher accuracy models improve lower accuracy models when they are averaged. We created a prediction model based on these 5 machine learning methods together with accuracy change data to select suitable model for accuracy change prediction. We evaluated each prediction model with 3 patterns of accuracy changes. These patterns are obtained by integrating models that are trained on 10 types of objects in CIFAR 100. The objects used vary for every pattern. Each prediction model is evaluated with mean average precision error. From this graph, support vector regressor has the lowest error. Thus, we used support vector regressor for the accuracy change prediction model. Then, we conducted model update simulation with FedTour. The purpose of this experiment is to evaluate efficiency of FedTour and the number of communication and updating model. In this simulation, we used actual user trajectory data in Spot. We also conducted a simulation with the gossip method that devices randomly select other with 10% probability. We evaluated the average, maximum, and minimum accuracy of all models after simulation and average and standard deviation of the number of updates of all models. We also checked the average accuracy transition when the limit of communication count was changed. We used point type flow population data as a trajectory data and extracted area including Nara Park, Todaishi Temple, and Kasuga Taisha Shrine in Japan. Trajectory data was sparse and included only a few percent of actual trajectory. So, we obtained 1,900 users data used on the 1 month of trajectory data as 1 day data. We assigned different training data and models to each of those 1,900 users' trajectory, and all the users updated their model with either FedTour or gossip method. All devices can communicate with each other when they are within 50-meter radius of each other. In this simulation, we used CIFAR 10. We used 10,000 of 60,000 images for checking model accuracy, and rest images as training data. Training data are augmented 10 times with some image processing, such as rotation. And model is VGG 16 that already runs ImageNet. Each user's model trained assigned data before simulation, and initial accuracy distribution is shown in this graph. As you can see from this graph, we obtained wide range of accuracy models. We conducted simulations using the initial model, varying communication limitation from 20 to 100. The main approach is to predict accuracy changes and resulting model accuracy based on the change. After the prediction of model accuracy, the tourist compares it with the threshold. Therefore, each tourist has to set their threshold that will be used to compare with the predicted accuracy of model after updating. For the threshold setting, we set the initial threshold to the median of initial accuracy distribution if it is originally below the median. Or we set the threshold to its own current accuracy if it was above the median to begin with. If the accuracy changes in simulation, it is set to a value a little higher than that accuracy if it goes above the threshold, and little lower if it goes below. We also set count of receive and transmission. In case of FedTour, we increase transmission in proportion to its accuracy because the higher the accuracy, the more demand there is for others. In case of gossip method, we set a half of limitation. This is one of the simulation results. First, result of average accuracy transition is here. The accuracy average tends to increase as the number of upper limits increases in both cases. And FedTour overcomes gossip method. However, the accuracy average saturates when the upper limit exceeds 70 times. We believe that this is because the more accurate each model becomes, the more difficult it to find a beneficial model. Here, we show the detailed accuracy and distribution when limitation is set to 40. From this distribution, each model concentrates higher accuracy with little variation in FedTour. Average, maximum, and minimum accuracy of models generated with FedTour is higher than those by gossip method. Also, minimum accuracy has been raised significantly, and maximum value overcomes initial one. Communication and updating in FedTour is only 3 times in average, and it is less than the gossip method. From these simulation results, FedTour achieves model improvement and reducing communication and updating rather than gossip method. We believe that the beneficial model selection and simple updating causes it. In conclusion, we propose FedTour, an approach which reduces communication and updating costs and improves model in tourist mobile devices. FedTour consists of 2 approaches. Sub-approach uses weight parameter for simple communication and updating. Main approach is to predict accuracy of updated model to avoid unbeneficial communication. We conducted model updating simulation with actual trajectory data. The simulation shows that our method can reduce communication or updating count and improve its tourist model. Thank you for listening.